Chemical Index of Alteration, Nesbitt and Young, 1982. September 12, 2021. Christian S. The Chemical Index of Alteration, CIA, after Nesbitt and Young, 1982, is possibly the most widely accepted weathering index for rocks. In this article, you will learn how to calculate it, correct for non-siliciclastic chow, as well as some things to keep in mind when interpreting the values and ternary diagram. Background. The chemical weathering of siliciclastic rocks has a strong effect on the major element composition and the associated minerals. The composition of upper crust rocks is dominated by plagioclase, quartz, K-feldspar, volcanic glass, biotite, and muscovite, Nesbitt and Young, 1984. With quartz being a stable mineral, the other components are rather unstable. The cations Ca, Na, and K are released during chemical weathering into weathering solutions. The Chemical Index of Alteration, CIA, is a good measure of the degree of chemical weathering. High CIA values reflect the removal of labile cations, such as Ca2+, Na2+, and K+ in relation to more stable cations, such as Al3+ and T4+, from the rock during chemical weathering. Conversely, low CIA values suggest low weathering effects on these cations. Nesbitt and Young, 1982-1984, used the general acid-based reactions, usually H2CO3, during weathering of feldspars and volcanic glass and investigated the kinetic behavior of these minerals. Feldspars commonly weather to kaolinite and alite, while mafic minerals and igneous glass weather to smectites and clay minerals, e.g. kaolinite and alite. They developed a framework of compositional changes of minerals during weathering, which can be used to predict weathering trends based on Al2O3, chow, Na2O, and K2O. Furthermore, this is expressed in the calculation of the CIA, which in turn can be visualized in a ternary diagram, Figure 1. How to calculate the Chemical Index of Alteration. As explained above, the Chemical Index of Alteration, CIA, is an expression of the proportions of stable Al versus the labile Ca, Na, and K. The formula is as follows. Chemical Index of Alteration, CIA. CIA equals Al2O3 / Al2O3 plus chow asterisk plus Na2O plus K2O, x 100. The oxide units in the CIA formula are in moles, not in weight percent, and chow asterisk represents chow in the siliciclastic fraction only. Important. The Chemical Index of Alteration, CIA, is based on molecular proportions. Therefore, in the first step, all oxides need to be converted into moles, and in the second step, chow might require correction for non-siliciclastic chow, e.g. from biogenic apatite and/or carbonates, such as calcite and dolomite. Conversion of weight percent to moles. The CIA is based on molecular proportions. That means the oxides, usually expressed in weight percent, Wt%, need to be converted into moles. Al2O3 moles equals Al2O3 Wt% / 101.96128 G/mole. Chow moles equals chow Wt% / 56.0774 G/mole. Na2O moles equals Na2O Wt% / 61.97894 G/mole. K2O moles equals K2O Wt% / 94.19600 G/mole. P2O5 moles equals P2O5 Wt% / 141.9445 G/mole. CO2 moles equals CO2 Wt% / 44.0095 G/mole. Corrections of Chow asterisk for non-silicate Chow. The correction of Chow to Chow asterisk, i.e., to the siliciclastic Chow only, is difficult and often impossible without reliable data for present carbonates and/or inorganic CO2. This is the weak point of the CIA and other weathering indices relying on a corrected Chow. Nevertheless, there are correction attempts as follows. 1. Fito et al., 1995. Following the below formula, Fito et al., 1995, the correction of Chow asterisk appears to be straightforward. The authors correct Chow for apatite using the P2O5 concentrations and for calcite and dolomite using CO2. Chow asterisk equals mole Chow, mole CO2, calcite, 0.5x mole CO2, dolomite, 10/3 x mole P2O5, apatite. This, however, causes a common problem with the CIA. Most chemical analyses do not include CO2, and even if it is not necessarily clear how much is hosted in carbonates and how much in organics. 2. McLennan, 1993. McLennan, 1993, proposed an empirical correction assuming Chow, silicates, equals Na2O if the number of Chow moles after correcting Chow for apatite is greater than that of Na2O. 3. My suggestion. If anhydrite or gypsum is present in S or SO3 concentrations are available, e.g. from X-ray fluorescence, XRF, Chow can also be corrected for this. Chow asterisk equals Chow, SO3, Ani/gyps. Figure 1. The Al2O3, Chow plus Na2O, K2O, or short ACNK, diagram highlighting some weathering trends, see explanations below, and general mineral compositions. Hint. Ternary diagram. If you need a ternary diagram, I wrote an article that explains how to build your own ternary diagram in Excel. Interpretation of the CIA diagram and values. Important. A word of caution. The CIA was developed for weathering profiles and prediction of weathering trends of igneous rocks. Although the index is often applied to sedimentary rocks, grain size distributions and sorting can have a strong effect on the CIA. For instance, fine-grained sediments might include a higher proportion of clay minerals than coarser-grained sediments, such as sandstones, affecting example Al2O3 concentrations. In addition, like Garzanti and Resentini, 2016, point out, the mineralogy and consequently the geochemistry of sediments may undergo substantial modifications by diverse physical processes during transport and deposition, including recycling and hydraulic sorting by size, density, or shape, and/or by chemical dissolution and precipitation during diagenesis, requiring caution when interpreting chemical weathering indices. Garzanti et al., 2013. There is a good match between theoretical and experimental results and geochemical data from modern weathering profiles when plotted as molecular proportions on the ACNK diagram. Early weathering stages are characterized by depletion in Chow, Na2O, and K2O, feldspar dissolution, resulting in trends subparallel to the CNA axis, green and blue arrows in Figure 1. Mafic igneous rocks, such as gabbros, contain plagioclase and weathering trends plot close to the CNA axis towards the smectite composition, green arrow in Figure 1. Felsic rocks, such as granites, on the other hand, contain K-feldspars. Their weathering trends, still subparallel to the CNA axis, plot towards a light on the Ka axis, blue arrow in Figure 1. Later stages of weathering are characterized by further K2O depletion with data trends plotting along the Ka axis towards kaolinite and/or gibbsite, orange arrow in Figure 1. Some initial CIA values for different igneous rocks. Basalt 0 to 45. Granites and granodiorites 45 to 55. Idealized muscovite is almost equal to 75. Elite, montmorillonite, and badolites is almost equal to 75 to 85. Kaolinite, gibbsite, and chlorite close to 100. Some CIA values to estimate the degrees weathering. Less than 50 to 60 initial stages of weathering. 60 to 80 intermediate degrees. Greater than 80 to 100 extreme degrees. A final suggestion. Fido et al., 1995, point out the effect of potassium metasomatism on the CIA values and suggest a K-metasomatism correction. See reference for